Welcome. Today's topic is inference. In terms of our overview of the course, we covered probability theory, which gave us a lot of language in order to be able to describe basically where data come from, some abstract notion of where data come from. And then we've been moving on to the problem of statistics, which is, okay, well, we observe the data. How can we use all of those abstract notions about data generating processes and what it is that we're trying to ask about our population and whatnot to actually use the data to figure out what we want to know about the population? And obviously, we don't have the entire population, so that's hard. And we saw last week that we can try to estimate quantities. And this week we're going to talk about inference, which is how do we quantify how bad our estimators are, essentially. So let's review a little bit from last week. When we talk about an estimand, that's a population quantity. Okay, so you might imagine you have a population. Let's say we're having an election, and some proportion of people are voting for one party, and another proportion are voting for another party. So you may want to know what is the total vote share going for a particular party in the population. So maybe you go and you survey some people and you ask them, who are you planning to vote for? So this is the kind of data you might get. And you can estimate the proportion of people in your sample who are voting for one of the parties versus the other. But that proportion is not necessarily going to be the population proportion that you're after. So how do you know how far off you might be? How do you know if those estimates are any good? That's kind of what we're going to talk about today. So the fundamental problem is that we only get to see one realization of the estimate. Right. So here these different little tables represent different samples that we could have drawn from the population or distribution, however you want to think about it. We only get to see this one sample. So if we had all these other samples, we could generate the sampling distribution of our estimator, which would tell us kind of the range of possibilities, the range of answers that we might have gotten under different circumstances, and that could be used to quantify our uncertainty in our answer, but we don't know what that is, and that's the issue. So how do we communicate the uncertainty? So let's start out by looking at a particular case, perhaps the simplest case that people think about in statistics for the most part, which is doing inference for a population average. So it's often the case that you want to estimate a mean from IID samples. So for example, the proportion of people voting for one party, that's just if you think of that is like a binary variable, like are you voting for this party or not, the mean of that is the proportion of people who are voting for the party that is indicated with a 1. So that's a common case. And so we observe some data. We talked about last time that a very sensible way to estimate a population mean is by taking the sample mean. We know it's an estimate, right? This sample mean is not going to be the same number as this population mean, except in very rare circumstances. But we want to know how bad, right? How far off do you think we might be? So another way to put that into words is if we knew the whole sampling distribution of this thing, right? What is the sampling variance of this, right? That would tell us how far off this could be from the true value. So the process is going to be this. We have our estimand. It's what we want to know. That's the true expectation of this variable z. We have our estimate. That's our guess based on the data for what this number is. And what we said on the last slide is that something that we might want to know is how variable our guess is. And of course, our guess, we only get to see one guess, right? So it's not like there's that particular number is going to change. But if we did the experiment again, our answer would be different. So that's what we're trying to quantify. How different would our answer be if we tried to replicate the result that we got? That's what we want to know. So that is the true variability of our guess. It's the standard error of this sampling distribution. And in this situation, it turns out that we can do this analytically. We'll see it gets a little bit more complicated in other settings, but in this case, I can just show you analytically what the sampling distribution or what the variance of the sampling distribution is. So the first thing to realize is that this thing here, our estimator, like we talked about before, so this is our estimator. This thing itself is a random variable. So it's I've taken all of these random variables and I've just mashed them together in a particular way to get this other random variable. It's a sum of random variables and then divided by some constant. So this thing is a random variable, and so it makes sense to ask about what its variance is. So we can do that. So all I've done is I've plugged in what the definition of psi hat is here. Here we're using the sample mean. So we put the sample mean in there, and now we can just proceed algebraically. So the variance of a constant times something, we can pull that constant out if we square it. That's simple enough. And now we have this variance of a sum. And you may remember that the variance of a sum of random variables is typically the variance of each thing. Like if you have two random variables, the variance of the sum of them will be the variance of each of them added together plus 2 times the covariance of the two random variables. But there's a special case when those variables are independent, their covariance is 0, so we can ignore it. And that's what we're going to do here. So each of these zi's, so these are the observations made across different people in our population. And under the assumption that those observations are independent, then we can pass the v in through the sum. So it looks like this. So that is an assumption that we made there about IID, but for the purposes, or independence specifically, but for the purposes of this course, we're focusing mainly on the cases where that is a reasonable assumption. Like I've said a couple of times, there's many cases when that's kind of not right. If you have a strong social network effect or contagion or things like that, that's a less reasonable assumption to make. But we'll keep going with this here. By and large, most studies and setups, you assume IID observations. Okay, so now we're here, and now we have this 1 over n squared sum 1 to n of variance of zi, and now we've assumed that the zi are IID. Part of that was independence, which we used to get from here to here, but now we also use that they're identically distributed. So that means that the variance of z1 is the same as variance of z2, is the same as variance of z3, because they all have the same distribution. That doesn't mean that they don't have the same value. So z1, z2, z3, different people have different heights or different voting preferences, whatever. But they're all identically distributed. So they all have the same variance. And so if we're adding up n copies of whatever that number is, that's just n times whatever that number is. And now lastly, we can cancel the n with this n, and we end up just with this. So here z represents the generic distribution of each of the z1, z2, z3, etc. And this is what we've got. So what we have here is an expression for the variance. This is, recall, the variance of our estimate of the population mean. We know that it's going to be as variable as any one of the individual observations in the population divided by however many samples we get. Okay, and as a side note, this is why we spent time learning all of the algebraic rules of expectation, the concept of variance, all of that stuff. Like you see, to kind of understand this relationship, you need to be able to do that. Okay, so let's try to zoom out to the big picture again. So we have our estimand. It's what we want to know. We want to know the population mean. We don't have the population. What do we have? We have the data. From our data, we can guess. We make a guess of what the population mean is. But now the problem is our guess. We know it's wrong, but we want to know about how wrong do we think it might be. How variable is our guess? If we were to repeat this experiment, how different would our answer be, right? Because that gives us some sense of how sure are we that this guess is good. If we expect to get wildly different answers from one survey to the next, then I'm not really going to believe whatever number I have, right? However, if I were to repeat this experiment and I'm going to get the same number every time, then I'm going to believe that this is a good guess. Okay, so in order to quantify that variability, we ask what is the standard error of this guess, and by doing the math that we did on the last slide, we can show, actually in this case exactly, that the standard error of this guess will be whatever the variability of z is. So the population variance of our measurement, so let's say the z is like voting preference. So it's the population variance of that divided by however many samples we used to estimate our sample mean. Now, problem here, for those of you who are astute, it's subtle, but the problem here is that we actually don't know this number either, right? We don't know what the variance of z is in our population. This is another population quantity. So that's actually why it's here on this side of the slide and not on this side of the slide. So this is a number we also don't know. So what we need to do is guess what that is, okay? So we need to estimate the standard error. That is our guess of the variability of our guess of what we care about based on the data. And so here we're going to use a plugin again. Right? What do? We just instead of the population variance, we just use the sample variance as a guess for what that is. And when you do that, you could write this as 1 over n times this thing over n, but I just put the 1 over n and the other n as n squared. So it's the same thing. Now here and here I have this mu hat. This mu hat is this thing, the sample mean. So you could just take this and put that here, because again we don't know the sample mean, so we have to use our estimate of that. And now this is our estimated standard error. This is our guess of the variability of this guess based on the data, and that is what we do. So that's kind of more conceptually or mathematically. In terms of code, this is what it would look like. If you had the population data, which we never do, right? But if you had it, to calculate the estimand, what you would do is just take the mean of z in your population. Now, if we just had some sample of data from this population, our guess for this sample mean would just be the mean of z in this subsample. And the standard error, the variability of this guess across different data sets, is given exactly by, in this case, the standard deviation of z in the population divided by the square root of n, where n is how many samples, how many rows are in this data set. Now we can't get at this because we don't have the population data, but we do have the sample data, and we're just going to do the same thing. We're just going to take the standard deviation of z, but in the sample that we get, and divide that by square root of n, and that's going to be our guess of what this thing is. So one of the key points here, which I'm going to get into again, is that this is an estimand, right? This is the estimand that we care about, but this is also an estimand, it turns out, right? It's just a different estimand. It's the estimand relating to the variability of our guess of this estimand, and then we have another estimate of this estimand. Yeah. So let's actually do it based on real data. Let's compute these things, and so we can see what it feels like mechanically. Okay, so it's the data that we're going to use come from this medical data package. So you can install that if you don't already have it. And then I'm just going to rename the data set to just be called data. And what we're asked to do here is to estimate the population mean age and population mean total intubation time with sample means. And then also estimate the standard error of both of those estimates. So let's first look at what the what's in here. So I think we probably have a variable called age. Okay, yeah, age. And then the other thing we're asking about is total intubation time. Okay. So to get the sample mean, which is our estimate of the population mean of those things, we can just get the mean of age and the mean of total. Okay, so these are our means. So the mean age in this sample is about 50, a little less than 50, and the total intubation time, I think this is in minutes. So these are people who are undergoing a particular kind of surgery. So this indicates that I think it's like most people are intubated for about 37 minutes in this sample, right? But what we want to know is, in the broader population of people who are undergoing this surgery, what is the mean age and how long are people generally intubated for? in that broader population? I know these are the numbers for the sample, but what is that? Are those actually informative about the broader population? That's the question. So in order to do that, let's calculate the standard error of these estimates. Well, we know that if we had the population data, the standard error of those estimates we could get by, according to what we did on the last slide, would be like this. Well, it would be like n, right? Where this is referring to how many people are in the population. We don't have the population, but we have the data. So we're going to just use the data as a surrogate and construct the plugin estimator. So this is let's first just define n before we do this. So we have 99 people in this data set. And let's use the formula that we derived here. So this is the standard square root of variance over n, or alternatively, the standard deviation of z divided by the square root of n. Standard deviation of my variable divided by square root of n. And then same thing for total intubation time. Sorry. There we go. Okay, and let's look at our original estimates again. Okay, so these are the estimates of the mean age, and this is our estimate of total intubation time, and these are the estimated standard errors for both of these measurements, the corresponding estimated standard errors. So based on that, the question here is, which of the two sample means do you think is closer to the true unknown population mean for that quantity? In other words, here, I have an estimate of the population age, an estimate of it, right? An estimate of the total intubation time in the population, and based on these numbers, which of these two numbers do you think is a better guess, is closer? So they're not both estimates of the same thing, right? But I would say that I'm more comfortable saying the population mean age is 50 than I am saying the population mean intubation time is 37, right? Because this standard error is bigger. And so if I redid the experiment, what this tells me is that I very well could have gotten a number here like 39. I very well could have gotten a number here like 35, maybe 34, something even bigger than that. Whereas here, I'm not very likely to have gotten a number that's too far off from 50 or 48. So this number is probably a better guess than that number is for the mean age. This is a better estimate of the mean age than this is an estimate of the total intubation time.